So I think it's time 9:09. So good evening once again to everyone, and welcome to week 12 of our night class. Hope you guys are preparing for your exams very well, Sha. So we are in week 12 for physics, and our topic for today's week is going to be light and optics. I think this is one topic that I think this is one topic that is going to be very interesting. I think it was one of my favorite topics then in school because it was relatable. So we'll be treating optics today, light and optics. So I think I wanted to say something. Maybe if I remember. So as usual, if you have anything to say, just turn on your mic and just call my attention so that I will be able to hear you and give response to you because I would not be seeing your chat in case you're choosing to drop your message or whatsoever question you're asking as a chat. So I'm saying this in regards to those people that are probably not familiar with the mode
Sawonite
of
tupu
operation
unu
here.
gị biko.
Okay, so as I was saying, let's just head into the lesson for today. So this topic will be treating light and optics. So optics is that branch of physics or that branch of science that tries to study light and its interaction with matter. It's that branch of science that tries to study light and its interaction with different forms of matter, whether it's solid matter, liquid matter, or gaseous matter. So there's that what optics we're be studying about. So we'll see different scenarios where we examine how light move from solid to liquid to vapor or to gaseous phase. So another definition I think I'll be trying to expound on is light. Light is actually known as a wave and a particle. So, though this is a general phenomenon that is experienced by all waves, they believe that scientists believe probably in advanced level physics. They said all um, all forms of waves exist as both particles and as waves. So light is not an exemption to that. So light exhibits both wave-like properties and also particle-like properties. So what does this mean? Light is said to have frequency, is said to have wavelength, and it also can be seen to act as matter. It's said to have a unit mass. It's like it can have a unit, like a unit. I don't know how I used to explain it, but an entity it can exist as an entity called photon. So light, they can exist as waves, that's something like this, continuously moving like this, and they can exist as particles. I think I mentioned something that they will move it as a stream of particles. So when they are seen in that form, they are called particulate form. When they are seen as wave, they are taking the form of wave. So geometrical optics deal with the propagation of light, including refraction, reflection, and their effect on image formation. So I think this is going to be one of the bases for our study so far. We'll be treating geometrical optics, seeing how light behaves in 3D objects and how it travels, how it bends, and how it behaves as it moves from one phase to another. So let's move on to the main portion of the lesson. So as I said, geometrical optics involves the study of light as rays that travels in a straight line. So it's the study of light that you are trying to study light and assuming that light is just a wave traveling in a straight line. So there is this law that says that it's called the law of rectilinear propagation of light that states that light travels in a straight line. So this theory is true. It's true in some conditions, but in some other conditions, maybe advanced level, it does not hold true. There's something that they call like bending of light. But for this point now, we are seeing it that light is assumed when we're talking about geometrical optics, we assume that light is moving in a straight line. So this geometrical optics tries to explain phenomena like reflection and refraction. So first off, I don't know if it's part of this, but let me just mention this beforehand. Reflection is when light is said to bounce off from a surface. When light is said to bounce off from a surface, that it hits a particular surface and it bounces off, does not penetrate the surface, it hits it and bounces off. And this kind of thing happens usually in mirror-like materials. When you see light being transversed or being sent or incidented on a surface, a mirror surface, it always reflects. It always go back, like to bounce back. So this phenomenon is different from refraction. Reflection and refraction. Reflection is when light hits the surface at a particular incident angle and bounces off at another angle, that is the reflected angle. So for refraction, it's a phenomenon where light gets to a surface and it does not bounce off, but it penetrates that surface. It's coming from a particular point, then it gets to a surface and penetrates that surface. But as it's penetrating, it bends. It bends as it strikes the surface. It's as the thing tries traveling inside the surface, it bends. It does not travel at sorry, it does not travel at the initial angle that it was incidented at. It's bending. That bend is called the refraction. The bending of light as it moves from one phase to another is called refraction. So refraction is always when it's talking about bending of light when it moves from one phase to another, usually from gaseous phase to solid or liquid phases. But there are still cases where it moves from solid phase to liquid or vapor phases. So it's just the movement. It's when you talk about refraction, it's the bending of light when it moves from one phase being solid, liquid, or vapor to another phase being solid, liquid, or vapor. So in the case of reflection, there is a law that is called the law of reflection. And in the case of refraction, there is also a law that is called the law of refraction. And these two laws are very, very important laws when you're talking about optics, because they would help you to understand how images are being formed and how we even humans are able to see.
Sorry, so for taking you aback.
Yeah,
And that refraction, you said that is from one phase to another. But the phase, is it from liquid, solid, and air, or what?
yeah.
Just
Any
clarify
phase,
me.
it could be from solid to liquid, it could be from liquid to gas, it could be from liquid to solid, it could be from any phase, just from one phase to another. But it does when it's changing phase. It's called
Okay,
and light bends, so it's called refraction.
okay.
Yeah, thank you. So now moving on, we are trying to focus now on reflection. Okay, so this is I said refraction is when light bends as a result of moving from one phase to another. So then I was explaining about reflection. I tried explaining them and giving the laws. I was thinking everybody was still hearing me. I did not know that I was off. So reflection occurs when light strikes a surface and bounces back into the same medium. So that's what reflection is. When light hits the wall and just do something like back to center, it hits the wall and bounces off like as though you're throwing a ball to the wall and it bounces back towards you. That's what reflection is. Light does not penetrate into the surface. It hits the surface and bounces off from the surface without penetrating. That's for um, reflection. But under refraction is different. For refraction, the phenomenon is different. I will explain that when we get there. So the law that governs reflection is known as what they call it, the law of reflection. That's the law that governs reflection. And the law says that an angle of incidence is always equal to the angle of reflection. As the angle of incidence is always equal to the angle of reflection. Can you guys still hear me?
Yes, sir.
Okay.
Okay. So the angle of reflection is always equal to the angle of refraction. And This angle is given as theta I for angle of incidence. Angle of reflection is theta R. So the angle of incidence is always equal to the angle of reflection. Reflection. In case I mistakenly said refraction, it's reflection. So it's usually seen in mirrors. We can tell. At least I think that one, this reflection is common. We know about reflection. So now for the law of reflection, it can be written simply as this: theta I is equal to theta R. So this is the simple expression for the law of reflection. So now moving on to refraction, the law that governs refraction is called the Snell's law. Snell's law, that's the law that governs the refraction of light. So as I said, refraction occurs when light travels from one medium or one phase into another medium or another phase. So that was the law is that was the that's when you observe refraction. So the reason for this bending is because of the change in speed of light, like changing the speed. So as the light is moving from one phase into another phase, the speed could either reduce or increase. So if it's moving from a solid medium to a vapor medium, like from solid to air, maybe from glass to air, the speed of light will be faster because in solid it's difficult to move inside solid, but as it comes out, particles of air are far apart and they're not really compact like in solid, so it moves faster. So on the other hand, for it can be the same thing when it's moving from, it can be the opposite when it's moving from air to solid. It will first have an initial angle, then to bend inward, shrinking. So as I said, the law that governs this refraction is called the Snell's law of refraction, and it's given as this: n1 sine theta equals n2 sine theta. N1 sine theta equals n2 sine theta, where n1 and n2 they represent the refractive indices of the two mediums, either from air to glass or from water to air or from water to glass, just something like that. They refer to the refractive index of these different mediums. So this law is usually is mostly used in determining the refractive index of materials with unknown refractive index. So it's important that everyone should take note that the refractive index of air is 1. The refractive index of air as it moves from air to water is, so if the refractive index of air is 1, while the refractive index into water is known as 1 point, is given as 1.333. So that's the refractive index. So, but you can determine the refractive index with the Snell's law still. As me, you know the angle of incidence, you know the angle of bend inside the water. Sorry, the angle of light bending inside the water. You can be able to tell the refractive index of the water. So, but usually it's always 1.333. So now let's see an example of questions under refraction. So it said light passes from air into water at an angle of 30 degrees. Calculate the angle of refraction. So they're asking for the angle of refraction. We already know from theory that the refractive index of air is n1, that is 1, and the refractive index of water is 1.333. So we can put that in the formula, in this formula here. We know our n1, we know our s1, we know our theta 1, sorry, because they gave us that the angle of light, the incident angle was 30 degrees. So putting that, you have this 1 times sine 30 equals 1.33 times sine theta. So that's the angle of refraction we're looking for. So plug and play, you will get your final answer to be 22.02 degrees. So this is how the questions come up under this topic. So they could either tweak it in whichever way they feel. They might try to remove one angle, or they might try to remove the refractive index. They might tell you particular glass, and they'll say you should find the refractive index. So does anyone have any question?
Yes, sir.
Okay,
Which
I'm
where
listening.
Okay,
You said
the light passes from air to water. So the
yes, it moves
incident
from air to water. The incident
uh,
angle is 30 degrees.
and the refractive um
The refractive index of water is
what
1.33.
is
The refractive the refractive index of
of
air
air
is 1.
one. What of the
Yes, is
sign
1.
there? Anyone
Sine is
sign
sine,
it?
like sine, cosine. Sine is sine, cosine, tan, all those kind of that was it is for you. So sine theta here.
Okay.
So if you plug and play everything, you will get your final answer as 22.02.
So what we are looking for is the angle of refraction.
Yes, the angle of refraction on the glass, I mean on the water, sorry. Angle of refraction in the water. So that's what it is. So now let's hurry up because of time. So next, there is what is known as total internal
I have
reflection.
question there. So I have question there.
Okay, I'm listening.
What we are looking for is theta, but from the question there is sine theta. So how do we get theta alone?
Okay, okay, you will take the sine inverse. From here, when you solve this now, if you solve this now, you will get from here, you get sine theta equals to this. Sine theta will be equal to 0.375. Sine theta here will be equal to 0.375. So if you take sine inverse of 0.375, you'll be able to get this as your theta.
Okay, thank you, sir.
You're welcome. So now, as I was saying, there is what they call total internal reflection. So this total internal reflection is what is a phenomenon that occurs when light travels from a denser medium to a less dense medium. You get, so this is the thing that happens when light travels from a denser medium to a less dense medium. So according to what I have, I said this is what it occurs when is traveling from a denser medium to a less dense medium. So it occurs when light traveling from a denser medium to a less dense medium strikes the boundary at an angle greater than the critical angle. So this total internal reflection is this case. So you might see this kind of stuff as objective question where they would ask you, or even theory question. They'll say, define the following TIR, and you would wonder, what's TIR? I don't think they mentioned something like that to us. So it actually represents total internal reflection, and it is that kind of point where the light it happens mostly when light is moving from either solid to air or from water to air. So it's from a dense medium to a less dense medium. So that's when you observe TIR, that's total internal reflection. Can you guys still hear me?
Yes, we can. Yes, sir. Yes, sir.
Okay, okay. So now when this happens now, the angle of refraction would be altered. The angle of refraction will be altered. Instead of it to give normal bend, because it's moving from a dense to a less dense, instead of it to bend inwards, because normally when it's moving from a less dense to a denser medium, it bends inward towards it. Because let me explain how refraction happens. Let's assume we had this block now. Let's say this is a solid material, and light is moving from air to the solid. Sorry, from air to the solid. They will draw the same straight line as we usually draw in glass. The same straight line, you draw it. Then as light comes to that point, this point where it touches the solid, we will draw a straight line. That line is called the normal. So then now, as because it's moving from air to solid, usually instead of it to continuously go like this, just straight inside, it will then bend somehow inward, like it will bend like this at a smaller angle. It usually bend at a smaller angle. So, but when it is moving from a dense medium to a less dense medium, what happens? You see something like this now. This is light moving, maybe coming at this angle from this dense medium. You draw the normal, light is coming like this. Then when it's coming here, instead of it to bend inward, it will bend outward. Can you guys still hear me?
Yes. Yes, sir. Yes,
So instead of
sir.
it to
Yes,
instead of
sir.
it to bend in, instead of it to bend inward, it will then bend outward. So there's a point where it will get to where it will bend, instead of it to come like this now and either bend outward. When total internal reflection occurs, when it will now bend, and instead of it to bounce outward, it will come here and still bounce inward again because of what they call um this TIR effect, total internal reflection effect. So the light would come in, bounce on its own surface, and go back like this. The same thing you should have seen in reflection. You will see it like this to bounce here, and instead of it to go outside, it will not go outside. It's just going like this, come back and stay inside the same medium. So this phenomenon is what is known as total internal reflection. So from what I have here, I said it moves from a denser medium to a less dense medium, and it strikes the boundary at an angle greater than the critical angle. So now when it moves like this and it comes parallel to the to this material, this is the horizontal line, it comes like this and it comes parallel. This angle I think creates a critical angle. That angle is when it's called, is what's called a 90 degrees angle. That angle is called a critical angle. When it creates 90 degrees to the horizontal, it's called critical angle. So now when the angle is down greater than the critical angle, is what when you can now see something that is like total internal reflection. I don't know if anybody is getting me or somebody is confused.
Sir, please, can you come again?
Can-
Please, I did not get it. Will you explain it again, sir?
Okay,
Thank you.
okay. So this is it now. We have light coming. Let's assume this whole page is covered by this block here. This blue something here is blue. Just imagine that this everything here we are seeing is blue, so that I'll have space. So light is now, we are now seeing light inside. Let me see this box. Light is inside this box. From somewhere inside this, maybe this solid material is moving from here, moving from solid out to the air. So normally, because it's moving from a dense medium, solid is thicker than air. Because it's moving from a dense medium to a less dense medium, it would not bend inwards, it will bend outwards. So this is going to be the normal line that we know, normal that we always have. So light will move like this, and normally it's supposed to bend like this. Then we'll measure the angle between these 2 points here, between the angle of refraction and this normal. We would have known the angle of refraction like that. But now, because of it is moving from a dense to a less dense medium, it will then, this angle of refraction will expand. Instead of it to bend like this, instead of it to bend small, to bend wider outward. But there's sometimes when it will bend, and it will bend even to become 90 degrees. There's light will come like this and go like this, 90 degrees. So this kind of phenomenon where it come from a particular incidented angle and go on 90 degrees is called critical angle. The thing forms a critical angle. So then now there is now a worst case when instead of this light to now go and still stay in this outside air medium, it does not go outside. Instead, it will come and bounce off inside because of just it bounces off inside. So the normal is still here, but instead of light to go and come outside, it will not bounce off. It will not go out of this medium. It will bounce inside the same medium. So this kind of phenomenon where you see that as if light comes from a particular medium, and instead of it going to the external medium, it bounces off and stays within the same medium, causing a very large angle of refraction. That phenomenon is called the total internal reflection. I don't know if it's clear.
It's cleared now, sir. Thank you.
Okay. So this phenomenon, light does not refract, but instead it reflects entirely back into the denser medium. So the same thing we would have seen in reflection is what we'll now be seeing in this case. So this principle is used in fiber optics and prisms. So this is used in advanced physics. Yeah? So the idea of total internal reflection is the angle of refraction is so wide because of light traveling from a dense to a less dense medium. So it creates a very large refractive angle that then becomes equal to, that then become almost equal, like not equal, that then becomes that then seem like as if the light was never refracted. I can see the thing bounce in the same region as if it did not leave the region. Because normally refraction is when light goes away from from one medium to another. So now, because it is similar as if it does not go from one medium to another, it's bouncing here and go back inside the same medium. It is not seen as refraction, but this kind of case is seen as total internal reflection. So now, moving on, critical angle. So now, this is what I was trying to explain. Critical angle and total internal reflection. So the critical angle is the angle of incidence at which the angle of refraction is 90 degrees. So as I was trying to explain before, trying to talk about critical angle, when we have light moving from any medium at all, and as the light is going from one medium to another medium, either from solid to air to liquid or from liquid to solid, and it can be able to make the angle of refraction 90 degrees. Let's assume it is moving from, let's use this as water and air. This is water, this is air. So now we have the normal here. So light is moving from a less dense medium, or from a dense medium to a denser medium, from light to thick. It's moving from light to thick. So it's coming like this. Normally it will bend inwards. It will bend inwards because it's moving from light to thick. So now there is a way that this incident angle can stay. There's a way it could stay. And this refraction now would make, instead of light come like this and bend, it would now come and become at 90 degrees. Come like this and be at 90 degrees. So the incident angle that can make light, the refractive angle, to become 90 degrees is called the critical angle. So I can say that is a simple way I can describe it. The incident angle that can make the angle of refraction 90 degrees is called a critical angle. So the angle of incident that can form an angle of refraction of 90 degrees is called the critical angle. So anything that goes beyond this critical angle is what would then be seen as total internal reflection. What we now see as total internal reflection. So the formula for critical angle, there's a formula, sorry. There's a formula to always determine the critical angle for,
Sorry.
yeah, I can hear you.
So that the incident angle that can form an angle of 90 degrees is called what?
A refractive angle of 90 degrees is called the critical angle.
Okay. Okay, that can form a refractive angle of 90 degrees.
Yes, it's called a critical angle. So there's a formula that we can use to determine the angle of incident that can form a critical, like an angle of incidence, or an angle of refraction of 90 degrees. So that angle, the formula is this: sine theta equals n2 over n1, where theta is the critical angle. So the formula is
Ma,
sine
please off
theta.
your mic.
Okay, sorry, my.
So the critical angle now is the critical angle is that angle that allows for refractive angle to become 90 degrees. So the formula to calculate that is given as this: sine theta equals to n2 over n1, where theta is the critical angle. So it is like sine theta c is equal to n2 over n1. So this way you can be able to use this formula to determine what incident angle or what angle you could incident a particular beam of light at, and to give you a critical angle of 90 degrees, or to give you a refractive angle of 90 degrees. So that's for that. So we can see an example here where we are given n for air, so n for water as 1.33, for air as normal 1.0. Then they said we should find the critical angle. So we are now asked to find the critical angle. So the critical angle now is now just putting this formula into play. We know our n2, we know our n1, and we can plug it into this formula, and we'll be able to get the critical angle. So the critical angle in this case is 48.75 when light is moving from water to air. So they say from water to air. So N1 is going to be water. N2 is going to be air. N1 is going, because they say from water to air. So where they are starting from is going to tell you your N1. Where they are going to is going to tell you your N2. So pay attention to that. So before you go and say, okay, in the former questions we solved, one was up and this one was down. So because of that, everywhere I see this thing, I'll put this one down and this one up. So if the say is moving from air to water, your N1 would be for air, your N2 will be for water, because the first one is always going to tell you which is which. So that's that for that. So now let's move forward into the next portion of the lesson,
Sir,
which
please
is going
come
to talking
again. Is
about.
that our N1? Sir, don't bring. See that if it's going from air to water, our N1 is going to be the air and the N is going to be the water.
Yes, yes.
Thank you very much.
You're welcome. So now let's move on. So now we have lenses. We're talking about lenses. I don't know how many of you can still hear me.
I can hear you.
Hello.
I can hear you.
Okay.
We can
I
hear you,
can hear
sir.
you,
Can hear
sir.
you.
Okay. Okay. So now we have lenses. So under lenses, we know that there are basically two types of lenses. So lenses are transparent optical elements. So they are different. There is difference between mirror and lens. I don't know who can help me with the difference between mirror and lens. Anybody who can help me with the difference between mirror and lens?
Let me try.
Reflect, but
Eh?
Oh,
a lens does not
Lens.
reflect.
Lens can. Okay, somebody's talking. Sorry.
No problem. Ma. I said a
okay.
mirror reflects
It's-
light, but lenses don't reflect. They mostly refract light.
Okay. Okay. So who else has another difference between them? You are correct. You are correct. But I still need some other
I didn't
differentiating
hear what
factors
she said,
between.
though. My sister, repeat, though.
Okay,
She said.
sorry.
She
I
said.
said that mirrors
Eh?
reflect light, but lenses refract it.
I didn't get you. Sorry, I didn't get you.
I
She
said
said.
Mirror.
that
She said.
no, you can say it, sir, so she hear. Ma, if
Go
you
on.
off your
Go
mic,
on.
can
Go
hear
on.
her very well, though. I said mirrors reflect light, but lenses do not. They refract light.
Okay. So she said. She said. Mirrors reflect light, while lenses, they don't reflect light. Instead, they refract light. So she's correct. She's very correct. So I need a physical difference that you can tell between mirror. That you can say, okay, this one is a mirror, this one is a lens. A
I
distinguishing
think.
factor between.
I think
Uh,
lens can magnify, but mirror will show
okay.
the exact size of
Very
the
correct, still.
object.
Very correct, still. Very correct, still. And there's still something
The
I'm still
mirror,
waiting to hear.
mirror
You
is
said.
made up of glasses reflecting cold, while lens made up of
Mhm.
transparent glass or plastic.
Thank you. Thank you. That's what I
Why
was
one is
expecting to hear. So
a mirror and the
that's
other
exactly what I
convex?
was trying to hear. Yeah. So
Okay.
that's what I was trying to. That's what I was trying to
I
hear.
didn't get
We have.
her. I didn't get her.
She
Sister,
said.
please repeat.
Okay.
You.
She said mirrors are made up of glasses and a reflecting surface, while lenses are made up of just glasses in different shapes. So that's the major difference between
I
a
didn't get
mirror
you.
and a lens.
Sorry.
Okay, see what
Can
it
you
is. To
repeat,
make a
please?
mirror, to make a mirror, you just need a glass and a reflecting surface. It could be nylon. So taking glass, any glass, and taking nylon, transmitting that inside side of biscuit nylon, the silver coating nylon, any silver-like material or a reflecting surface, put it on top of a transparent glass, you've made a mirror. Just take your glass and put maybe biscuit nylon at the back of it, glue it to the back of it, you've made a mirror. So now you could make either a plain mirror, a convex mirror, or a concave mirror. So depending on how the kind of glass is, but you will definitely make a mirror. So, but for a lens now, is when you just have a glass, just a single glass. So that's what is the distinguishing factor between the. So now we have different types of glasses of lens. We have um, concave lens and convex lens. So concave lens has its own shape. Convex lens has its own shape. You get? I don't know who is still confused. Who is still confused?
No, I don't think anybody is still confused.
Okay, okay. So now
So we have
for
major differences now.
yeah, we have the major difference between a mirror and a lens is that mirrors they have tendencies just mirrors can magnify, mirrors can magnify and mirrors could also shrink. So that's why I was not really looking for just all those distinguishments that you were trying to give, or those distinguishing factors that you were trying to give. So plain mirror would reflect exactly as it is, yes. But a concave mirror would not reflect exactly as it is. A convex mirror will not reflect exactly as it is. You get? But the thing that is the major difference between a mirror and a lens that you can say, okay, this one is a mirror, this one is a lens. So I don't know the type of mirror, I don't know the type of lens, so, but this particular one is a mirror, this particular one is a lens. So it's when you add a reflecting surface to a lens, you get a mirror. When you add a reflecting surface to a mirror, you get, sorry, a reflecting surface to a lens, you get a mirror. So that's the major distinguishing factor. So concave lens, they are known, or concave lenses, they are known as converging lenses. Convex lenses, they are known as converging lenses. So we're talking about the one that does not have reflective surface now. We're talking about lenses. So that's the reason why I mentioned, ask for the difference, so we can be able to tell. Because if we don't know the difference between both of them, we might think we might be mistaking it. We might be mistaking both of them, but they're not the same thing. So concave mirror has its own it has its own convex mirror has its own. So now for lenses, now we're talking about, in this particular portion, we're talking about lenses. So convex lens, let me start with convex lens. This is what I'm talking about here. So I just hope I would not mistake or make mistakes by calling one of them the other. So convex lens or convex lenses, they have a kind of, they are usually the one that they know as magnifying lens. They are mostly the kinds of lens that they are seen as magnifying lens. So these convex lenses, they kind of curve outward. They curve outward, like they curve towards you. If you try to rub the surface of the glass or the lens that is facing you, it seems like as if it's bulged out, like as if it's pregnant towards you, like the stomach came out. That I can distinguish by feeling it. If the stomach comes forward towards you, it's known as a convex lens. When it bends towards you, it's known as a convex lens. So, but when it bends away from you, like it goes inside, like it's something like convex lens. Now, this is you here. You're looking at the lens here. So it seems like this lens is kind of curving towards you, like as if it's pregnant towards you, as it's facing you. It's a convex lens. But when it's like as if pump his stomach inside, or his stomach is bulged inside or pushed inside, it's a concave lens. It's a concave lens. So you can use the idea that caves are always kind of inside. Caves are inside. So you can use that idea to grab the idea behind concave and convex lenses. lenses, because when it comes to the other when it comes to mirror, it's almost different. So for lenses, concave lens bends inward, while convex lens outwards bends outward. So now, let me start mentioning some major characteristics of these two
Which
types of
one best
lens. Well,
outward, sir? Which one best outward?
the one that bulges outward is convex, while concave bulges in or it bends inward. So now let's just talk about some of the characteristics. So now write them, because these ones I did not write them here. So just write these ones down in your notes. So now concave lenses, they are said to have negative curvature. Curvature. They are said to have negative curvature. That's why they are called concave. So they are said to have negative curvature, while convex are said to have positive curvature. So concave lens are said to have negative curvature, while convex lens are said to have positive curvature. I don't know if I can go on.
Sir, please repeat again.
Concave lenses, they have negative curvature. Curvature, Curvature. Concave lenses, they are said to have negative curvature, while convex lenses are known to have positive curvature. Another thing is that concave lens, they are usually known as diverging lens. They're usually known as diverging lens. Concave lens, and they are also known as diverging lenses. And the reason why they say so is because when light bounces on their inward this their surface, the light, it will be spread outwards. It will spread outwards apart. So now, as maybe we had something like this, we had a concave lens like this now. A concave lens like this. It looks like it bends inward, both in front and in back. So it's like it's like this. I don't know if you are seeing the diagram I'm trying to draw. It's like this, a concave lens, or a two-side concave lens. It's looking like this, like something like an hourglass or figure eight. So now, when light comes on one end, incidents on one end of this concave lens, when it's coming out on the other side, it spreads out. It spreads out like torchlight. It spreads out. So that's why they're called diverging lenses, because when light comes in one way, it flees in 7 ways. So it spreads out. So when light comes from one direction, or in one straight line, sorry, in a straight line, it diverges, it bends light in other directions outwards. So that's how these concave lenses are. So that's how they work. So for convex lenses, they are known as converging lenses. So when you have a convex lens, these eyes look like this, something like a pear, something like this. It looks like this. It bulges out in the outside and bulges out in the inside. So these are convex lenses, they look like. So now when light comes towards it on one end, what happens is that it then shrinks light towards a point. It directs light to a particular point, making it um, focus on a particular point. So they are known as converging lenses. So they are known as converging lenses. So I think these are the major distinguishing factors between these two types of light. So they are used in different
Sir,
materials.
please take it again, oh, please.
Okay, I said concave lenses, they bend light outwards. When light passes them, like penetrates them and goes to come out from the other side, the light will spread wider, like to spread wider, like torchlight. You have them coming in like this, then to spread outside when it's going out, like funnel. They behave like funnel somehow. So while convex lenses, when light comes in towards them, When it's coming out, it bends towards a point. It focuses on a point, something like a cone. It focuses at a point. So that's how convex lenses work. So when light enters them on a straight line on one side, it comes out on the other side as a sharp arrow, something like that, on the other side. So it converges the light. So they are called converging lenses because of the this to light. They converge light when light is leaving them. So while convex lens, concave lenses, they are known as diverging lenses because they diverge light when it comes towards, when it passes through them. They diverge light rays when it passes through them. So now let's hurry. So now there is a formula that is known as a lens formula. I think this formula is popular to you guys. So long as we are, all of you should have seen this formula. 1 all over F is equal to 1 all over V equal minus 1 all over U, where our F is known as the focal length, our V is known as the image distance, and our U is known as the object distance. So this formula is known as the lens formula, and it is used to determine the focal length of different lenses. It's used to determine the focal length of different lenses, and can also be used to determine the image distance and also the object distance. It can be used to determine the image distance and the object distance. So the image distance, when you hear image distance, you're talking about the screen, the distance between the lens and the screen is what they call the image distance. But distance between the lens and the objects that they are viewing is what they call the object distance. Lens and screen, image. Lens and object. Lens and screen, image. Lens and object. So that is for
Sir,
this. So yeah, I can hear
excuse.
you.
You said distance between lens and screen is what?
Lens and screen is object distance. Sorry, image distance. Lens and screen is image distance, while lens and object, the distance between lens and object is called the object distance. So
Okay, thank you.
most of the times, object distance are usually farther than image distance. Most of the times. Most of the times. So this is the formula to determine that using the focal length. So now, moving on, we have an example here. They said a convex lens has a focal length of 10 centimeter. An object is placed 30 centimeters away from it. Calculate the image distance. So it's just plug and play. It's just plug and play. So as I was saying, these physics questions, the most important thing you can do for yourself is to memorize the formulas, because once you memorize the formula, sometimes they might try to trick it or bend it. But the main thing at the end, they will not bring a formula from the space to solve it. It's the same formula that you know that they would find to solve it. So now the more you get conversant with each of these formulas and you get to memorize these formulas, I think there was one time when I was trying to learn, when during my secondary school days, when I was trying to learn these stuff, what I was doing then was, once I see a kind of solving formula, I'll just carry the question. I'll know the topic that it is coming from. Every formula that is in that question, I'll just start one by one, using writing them in my book. Then look at which of them can give me an answer. Use it and solve, get an answer. Which other one can I solve again from that with the question that are there? Before you know it, that time I was not already as clear with physics ideas as the thing later got to be. Then I was not already knowing exactly what they were trying to talk about when they're asking questions. But as I was just looking, okay, I know this under optics, there are so and so number of formulas. They gave us question. This formula has this question, this parameter. So since this parameter they gave us is inside this formula, I'll use it and solve and get one thing. I'll use and solve and get the answer for that one. I'll be like, okay, now we've gotten extra something. I'll look for that formula that can solve something. Before you do it 5 times, you would have gotten the real answer. Before you do that kind of thing. Though it was a careless way to do stuff. So, but that I found that's the reason why I found that anyhow, just start from the smallest simple way you can solve out. They give you a question and they're asking you to find, maybe they're asking you to find something deep. The parameter they gave you, you don't even know which of them can give you that one. Just first, know all the formulas that are under that topic first. Then once you've known them now, just start solving them, picking them one by one. Okay, they gave you this one, they gave you this one, you don't know this one. You use the formula, the ones you have to get what you don't know. Once you've used what you have to get what you don't know, before you know, you've had more, you've gotten more. You now have more that you have now that you can use to get another one that you don't know. Before you try doing this thing continuously, you find out that you've gotten the answer without even thinking. The questions are not really difficult in physics because most of this level, secondary level physics or undergraduate level physics is not undergraduate level, pre-undergraduate level physics is usually basic. It's just usually highest 3 tweaks before you solve 3 times or use 3 formulas, you will get the final answer. Probably when you get to advanced level physics, you might be needing more complex formulas or you need to know larger exponential formulas. But for the basic level, before you do 3 solvings, you will get the answer they are trying to ask you for. So this was one of the things I found out then. So that's what I've been hammering on, knowing the formulas. So now, optical instruments. Optical instruments. So these are
It's actually
instruments.
a question for us now. Let's check the one we did, whether it's correct.
So I should give one question for you guys.
No, I said this one now. Solve it now so that we cross-check with
Okay,
what we
okay.
have.
It's here. The answer here is 15 centimeter. So this
Why
is the
is the
solvings here.
why is the 1/f minus?
Okay. What happened here is this. They did not put minus here. This thing is what we are seeing here. This dash 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 is ellipsis that is trying to show paragraph. It's not necessarily minus. Or are you going to call this minus using? This is not minus using. This is not minus solving. It's just an error that not really an error, like something that is not supposed to be there. But I was preparing the slide, all these bullet points kind of stuff. So it's not that this minus is representing -1 over this. It's just this here. It's just this. It's just 1 all over 10 equals to 1 all over v minus 1 all over. So the only time you will see minus is if you are probably talking about a diverging lens, because I said they have negative curvature. If you can remember when I said something like, okay, I did not write it here, but I said it when I was explaining that they have what they call it, diverging lens. That's concave lenses. They have negative curvature. So in that kind of case, that's when you might have a negative focal length. But in this case, most of the times you would always see positive values. Positive values. So that is not negative. It's not minus like this. This is normal plus. It's normal plus. I don't know if it's clear. Hello, can you guys still hear me?
Yes, sir,
Yes.
it is clear.
Yes,
Yes,
sir.
sir.
It's clear.
When you want to make when you want to make 1/b the subject of the equation now, eh?
Yes,
It
now
will
yes, we're trying to make 1 over v. Okay, see how okay, I think this kind of stuff it was confusing too at that point. When you have fractions, fraction throughout, when you're trying to move a fraction to the other side, you would move the entire fraction to the other side. So now we are trying to make 1 over v the subject of formula, right? So
yes.
we'll remove minus 1 all over u from this side to the other side. So moving minus 1 over u to the other side, we'll then be having 1 over f plus 1 over u, right? 1 over v will be equal to 1 over f plus 1 over u. True or false?
True.
We have 1 over f equals 1 over v minus 1 over u. That is the normal formula. So now we want to make 1 over v subject to formula. So to remove this fraction, we'll move this one here away from this point. But his number, his sign is negative here. Sorry, has a negative sign here. So when I'm moving this negative sign across an equal to sign, it will become positive now. So instead of me going as minus 1 over u, it will be going as plus 1 over u. So you'll now be having 1 over u plus 1 over f equals to 1 over v. Is it clear?
Yes, sir. Please, who
With that, if you should solve it properly now, you'll be having 1 over f plus 1 over u. Your f is 1 over 10 plus 1 over 30. So when you find the LCM and you get your answer, you'll be getting something as a fraction. Then note that that is not your final answer. You're having 1 over v as that answer. So you take inverse of both sides to get your ordinary v. So you flip both sides or take inverse of both sides to get a final answer, and you get a final answer to become 15. So you could solve it and see whether you will get that. But I think that's what you should get on your normal. So let's hurry up because of
Get it
time.
though.
Because yeah,
I got
you
I
say
didn't get 15, sir.
you got what?
I got 30/4,
30 over 4.
which is 7.5.
How do you get 30 over 4? You
I
you
did
should have 1 all over 10 plus 1 all over 30, right? So can you
that's
guys
what
still
I
hear me?
1/10 plus 1/30.
Yeah. So then what next you do is finding the LCM of 10 and 30. So once you found the LCM of 10 and 30, it will be your LCM. Then you use your LCM the same way you usually solve LCM. This divide this times this plus this divide this times this. So you'll be having something like, if you use the rugged way or the fast approach to do the LCM, you just multiply 10 and 30 that are the LCMs. 10 times 30 is going to give you 300. So the LCM will be 300. So 300 will be the base or will be the denominator. Then 10 in 300 is 30. 30 times 1 is going to give you 30 plus 30 in 300 is 10. 10 times 1, 10. So that you will now be having 30 plus 10 all over 300. 30 plus 10 will be giving you 40 over 300. So if you do 40 over 300, if you divide it, 4 all over 30. 4 all over, okay, you said you got 4 over 30, right?
7.5, sir. That is what I got.
Yes, I got. That's what
That
I
is
got.
4
4
over
all over 30.
30.
Over
So
30.
then you take the inverse of that. Take the inverse of 30 or 4 over
And
30.
then you equate it now. You equate it to 1/v, which will give you 4v equals to 30. V is 30/4, which is 7.5.
That's 7.5. Ah, how did I make that kind of mistake here? Oh, let me see. Hold on. Pardon me. Let me see whether I made the calculation error here. I think the only way I'm getting 15 is if I put a negative sign on this u. That's the only way I'm getting 15. I think from what I even have here. Okay, okay, okay. So I just observed my own omission. Like what happened was the answer here is still correct. So, but now there is this assumption that when the image and the object, I don't think I mentioned it earlier. So there's this belief or this conventional understanding, sign convention, that when object distance is on the same, when the object is on the same side with the image or the incoming light, the in the object distance would have a negative sign. But when the object is on the other side of, like, assuming you have a lens like this, and light is coming from this direction, and we have the object in the same direction of the light direction, the same side of the mirror of the lens with the, sorry, we have this object on the same side. I don't know, can you guys hear me? Hello?
Yes.
Okay, so when you have this the object on the same side with the direction of the light, you would have to give this object distance a negative value. So it's a normal sign convention normally that they say when you have objects on the same side with the direction of light, you will give it a negative sign. But when it is on the other side of the lens, it's going to take a positive sign. It's going to take a positive sign. So that is the reason why there should be this 30, the distance here should have a negative sign. Though to me, it does not really make sense. It does not make sense to me. Because the only time I can be able to tell that this is true is if I've carried out a practical to tell this. Because I know there's normally a practical that you can use to tell where the image would appear, depending on where the object stays. But now it's not adding up. Except you would have carried out the experiments, the normal sign, the experiment where they put an object, draw the line.
Excuse sir. Check the formula again.
The
That
formula is
formula,
correct. The formula is correct.
I thought it's minus 1 over f equals to minus 1 over b minus 1 over u.
No, the formula is correct. Formula is 1 all over f equals to 1 all over v minus 1 all over u.
So which
Formula is
formula
correct.
minus minus in all of them? There is one that has such formula.
Let me check. Let me check. Let me check. If I can find any textbook that has that formula. Yeah, it's still the same thing. I'm correct. Formula is correct. It is 1 all over f equals 1 all over v minus 1 all over u. So the issue is now, if you can remember in physics, when they will draw stuff like this, they will draw a straight line, they will draw a lens, and they will put an object, and they will now put maybe something like an arrow. I don't know if you guys did it in your school, and they will draw a straight line to the lens, and they will then be drawing lines that show the intersection to tell whether it's a real image or whether it's a virtual image or stuff like that. So that is the idea that is bringing this. I think when the distance of there is a rule. I think yeah, there's a rule from that stuff where when the distance of the focal length and the image distance they are twice or more than. I think I would send you an image for that. There should be a rule where you would write all those stuffs, all the possible scenarios where you could say when the image or when the object is close to the lens, closer than the focal length, or when the object is far from the lens or is on the focal length. Or I think there's, let me see whether I would find later after this class, I would send you an image. I'll send you an image that would depict this because I can remember clearly that that's when you can be able to tell automatically that okay, oh, because of this, you will give the u value a negative sign because from what I'm finding out, this u value is supposed to have a negative sign, and the only time that it can have that negative sign is when it has it appears on the same side of the when the image is on the same side of the screen, like the object, the image forms on the same side with the light, where the red light is coming from. When the image appears on the same region, they will give the u value, the object, the image distance.
When
Hello.
it says when the object is at the left, you take negative.
Yeah, when the object is at the left, right, that is on the same side with
Yes,
the image. On the same side with the when the object, is it the object or the image?
object is always on the left side, so it is negative.
Yes, it's always on. So when the object is always on the left hand side,
Yes, so it is negative.
so it's going to be always negative.
Yes, why the f is going to go with positive. It now be 1 over 10 is equal to 1 over v minus 1 over minus 30 is equal to 1 over v plus 1 over 30. That's how you get 1 over 15, which is 15. So it's still correct.
There is actually a rule. There's a rule that tells when, because there are times when you would not put that minus on the u. There are times when you put the minus on the u. I think I would need to immediately after this class. I would find that out and I would get it to you guys. I think I would find that out and I'll
Okay,
get it to you guys.
let's move on now.
Yeah. So let's move on. So optical instruments, we have different optical instruments and they are used in making mirrors and materials like microscopes. So lenses are preferably are what are using all this microscope, telescope. They don't use mirror. They don't use mirror. They use lenses in microscope. I think the only places that I've heard that they use mirror, or the only optical instrument that I know of or that I can pick at the back of my mind is a kaleidoscope and a periscope. So these two, I know that they use mirror at different angles for a this thing for a periscope. I don't know how many of you saw or have known about periscope. Sorry, about periscope. They said periscope they look like this. I think something like a Z shape. Periscope they look like a Z shape object where you would look from this end and you see something that's above. You look from the lower end and you'll be able to see something that's above. And they use it in um, submarines. They use it in all these trucks where the army people they would just raise the head of the submarine, just a single trunk. Is it trunk they call that stuff? A single end of the submarine just come up above the water, just like a stick outside the water. But that stick now, they will then be rotating it to survey around. Then they will be under the water. They don't need to come out of the water to see what is above the water. They just stretch that portion up. Then they would observe from inside and tell, okay, offside above the water is clear, or above the water people are outside, or something like just stuff like that. So materials like that, they are the materials that use mirrors, but lenses are used in the human eye. They are used in even correction of human eyes as well. They are used in I think telescope. Yeah, they're using telescope. They're using microscopes and also in camera. So lenses they are different. I've already explained the differences between lenses and um, mirrors. So now moving on to microscopes now. So microscopes are
No, sir.
made up of
No get
yeah
you. Said that mirror
yeah I can
is
hear you.
used. You mentioned two optical.
Not only not only, but I know I can remember just two. Mirrors are used in kaleidoscopes. Kaleidoscope. Kaleidoscope or something like that. Kalei. Kal yeah Lei or Lie. One of them.
KAD.
Lei. Kal. Let me confirm. Kalie or Leidoscope. Let me see whether it's
Kaleidoscope
which
and
one.
what?
Yeah, it's okay. Kaleidoscope. I was correct at the beginning. Lei. Kaleidoscope.
And what?
Kaleidoscope. And periscope. Periscope. So these are instruments that I'm very sure that they use mirror. So I know I've made a periscope before. I've made a periscope before, and I know of a kaleidoscope, but I've not really used a kaleidoscope before. So they are the ones that they use mirrors, and they use plain mirrors. So for a kaleidoscope, you can check it up how it looks like, but it uses two mirror at an angle of 60 degrees to one another, and that's what a kaleidoscope is. While a periscope, it's at an angle where the two mirrors are going to be at, and they are parallel to themselves, but they are kind of in a 45 degrees. So it's best to see it by via image. So it's best to see it with image. So you'll not just be hearing it from my mouth. Just when you maybe assignments for yourselves, just look at it, what it looks like. A simple periscope and a kaleidoscope. So just check what they look like. So now microscopes now, they are made up of two lenses, or they use two lenses. One of them that is known as the objective lens, and one of them that is called the eyepiece lens. So and these lenses they are used to magnify images. They are used to magnify different images or different objects, not images. They used to magnify different objects. So you say they have the object lens and the eye lens. So the object lens is the one that is closer to the organism you're trying to view, while the eye lens is one that is you are looking through. So the object lens is one that forms it forms an image that is magnified by the eye lens or the eyepiece lens, and the magnification is the product of the magnification of the object lens and the eye lens. So what happens? How this microscope is able to zoom things very well because since it uses two lenses, these two lenses they have very strong magnification. So the first one will do its own magnification, then the second one will magnify that one's magnified image. So once you've done that kind of double zooming, the images or the objects will become way clearer to the observer. So this instrument they make use of two lenses. So for telescope, I think they make use of three lenses, if I'm correct. So for telescope, so we have an electronic microscope and a simple microscope, if I'm correct. I'm not really sure of that, but I think we have just a
Compound. What we have is
yeah
compound microscope.
compound microscope. I think we have an electronic microscope as well too, but I don't really know much about that, Sha, but I know it's under biology. But we have compound, we have a simple microscope, we have compound microscope, and I think we have an electronic microscope too, or an electron microscope. It's either going to be an electron microscope, but I
Yes,
know there's one
electron
that
microscope.
yeah.
The one
So
that is used to view virus, because you
yes,
can't use
yes,
ordinary microscope to see virus.
yeah. So that those are the microscope that I know are they are the types of microscope. So now going to telescope now, they are made up of lenses as well. I think they are made up of three lenses. Telescopes are made up of three lenses. Then we have types of telescope. It could be either refracting or reflecting microscopes. I'm sorry, telescopes. Can you
What
guys
do
still
you
hear
say?
me?
But repeat.
Okay, I said we have two types of telescope: refracting telescope or reflecting microscope. So refracting microscope uses lenses, while reflecting so why am I saying microscope? Refracting telescope uses lenses, while reflecting telescope uses glasses. They use mirror rather. So
I thought we have three, which
telescopes, as I
is
was
the third
saying,
one, which is the compound telescope. Yes,
compound telescope. Yeah, if you want to
yes.
describe most of all these type of telescope, I would say there are many. If I would say there are many types of telescope, but there are some that are primary based on the use. So for refracting telescope, they use lens. I think this is one of the distinguishing type. So even if it's a compound telescope, probably that is using lens, it's a lens telescope. And if it's a compound telescope, I don't know if it's compound that uses glass and mirror too. It's going to be a compound mirror telescope. But now the major two types of telescopes are um, refracting telescope and reflecting telescopes. So where the refracting ones make use of lenses, while the reflecting one make use of this thing, make use of mirror. So the what they call it, they also have object lens and they also have eyepiece lens. They also have object lens and eyepiece lens. I think that there is a type that has like three. I think there's a type of mirror that's sorry, of telescope that has three. So basically, we just have two types of telescope. Basically, the main two distinguishing types of telescope are what they call it, refracting and reflecting telescope, where the both of them consist of um, two lenses or two mirror. So for the reflecting telescope is made up of a primary mirror and a secondary mirror. So this it uses a mirror in the place of lenses. So and it uses mirror to focus light, and the reflectors are the mirrors. So that's just the basic difference between what they call it, the telescope, the reflecting telescope and the refracting telescope. The type of material that they use to focus on light. One of them uses a refractor, while the other one uses a reflector. So I don't know if that's clear.
I can't
Hello,
get you.
can you guys still hear me?
Mm-mm.
I said there are basically two types of telescope: reflecting and refracting telescope. So the reflecting telescope makes use of a reflector, that's a mirror, while the refracting telescope makes use of a refractor, that's a lens. That's a lens. So they are used for observing celestial bodies. All of them, they are used for observing celestial bodies and looking at planets, stars. I think it's one of the things I would have loved to use a telescope. I would have loved to see or use a telescope. But I've not really gotten that opportunity. So now, I think with that, we will be going into just the experimental part of this lesson. experimental part of this lesson where we're talking about how Snell's law is used. I think if you've done what they call it, if you did physics practical previously, in your probably in your secondary school learning, you remember where they gave you probably a rectangular glass block. And I think one of the popular precautions will tell you, I ensured that I did not, I observed parallax error. That's one of the common error that they always saw, error due to parallax. That's one of the practicals that is crucial in that kind of stuff. So what this practical is about is you take a rectangular glass block, you place it on the table, on top of a white on top of a white paper. Take the block, place it on a white paper. Then you'd on one side of the block, on one end of the block, you'd when you put the block on the paper, you trace the edge of the block. You trace it on the paper. And once you've traced it, you then remove the block and draw a normal on one end of the block. Draw a normal on one end of the block. Then from that normal, you take an angle that you choose. Draw that angle to be your angle of incidence. The angle will be between the normal and the angle of light. So you measure that angle will become your incident angle. You put it as I. Put it as I, then you then replace the block so that you replace the glass block on top of the same square. It should fit in exactly as the thing was before. And once you've placed it back, you then come to this other end here. Come to this other end. You had the block, the normal drawn on this other end, and you drew the angle here. So on that angle now, you would put the pin. You put one pin on one of this line on the angle. You have your angle, the line like this moving slanted. So you put a pin as one spot on that straight line, making sure that this pin stands completely erect, like straight. Then you put another pin on the second line at the back of it and make sure that that same pin stands straight, like so that if you're looking at it from the other end, you will see them as just one pin. Stand them, make sure that they stand completely straight on the same straight line. So then once you've ensured that that has happened, you then come to the other end and observe those first two pins through the glass block, through this end of the glass block. You observe these two pins and place a third pin to obstruct those ones too, so that you will be seeing only one pin. Then you place a fourth pin also to obstruct all three, so that through looking at the fourth pin, you would see only one pin standing, because the fourth pin will block the third pin, the second pin, and even the first pin. So if you do this perfectly, once you're done, you can now remove the block and join the line on this other third and fourth pin. Join their line together to the block, the paper trace on the block. Once that's gotten there, you draw on that normal. Then you measure the angle. That's going to give you angle of refraction. I think it should give you a kind of angle of refraction. Oh no, once you've done that, you then that angle that is there, you measure it. Then you use I think the law of one of the trigonometric laws. You join this one here, then you join this one also to the point where the thing intersected here. So you can be able to tell the angle of refraction on the other end. It will be practical, it will be more explanatory if I were to do it physically. But for those people that have done the practical before, I think they can relate already by my explanation. So that's for the experiments to be able to practically do or determine the Snell's law. I think, I don't know, I don't want to make promises yet, but that's for that. So for the focal length of lens, I think there's another experiment, which is what I was trying to talk about, where you would draw a straight line, you place a lens, you put an object, then you put, the object can even be a candle, can be a candle. You would measure you draw a line, then you're trying to determine the focal length of that lens. So you start shifting the candle position, different positions, very close to the lens, far away from the lens, farther away from the lens, and far away from the lens. So that way, there are rules that tell that, okay, when the images are forming, if you form an image at the back of this lens, there's a principle that it tells. If you form an image at this point, there's a principle that tells. If you form an image that is infinite, there's a meaning to that. When you can get that image that is giving you infinity, that is going to tell you at that point that the candlestick is standing on is the focal length. So you can measure that point where the candle is standing that made the infinite image to the lens, and that will give you the focal length of that lens. So these ones are things that you do practically, not physically. So now applications of optics. We have in cameras, microscopes, telescope, fiber optics, and also corrective lenses. That's the eyes that we wear, and even people that yeah do fashion contact lenses. So they use optics in um in these materials. They use the understanding of optics in these materials. So I think that's going to be all for today's lesson. Because I was saying, I said there's something I would send to you guys on the group. The image that should show the different points. This practical. I think that practical will be able to, this practical is itself. This practical, this particular practical is going to help to solve why we were having this error here. It's going to clarify why we were putting the negative sign here. I said that we should put a negative sign here. So that image will tell us why we should put that negative sign here. So does anyone have any question? Does anyone have any question? Hello, can you guys hear me?
Yes, we can hear you, sir.
Yes, we can hear you.
Okay. Does anyone have any
So
question?
yes, in that refraction calculation, so how were we able to get theta two because to 22.02 degrees? See? Yeah.
Okay, what did you get as your own answer?
No, like I got 0.375. So I'm asking how did they end up at that? Like
Okay, see what
was
you
that
got
supposed
here.
to
So 0.375. So that's sine theta is equal to 0.375, right?
Yes.
So now you're not looking for sine theta, you're looking for theta. So you need to take sine inverse of both sides. So if you take sine inverse, the sine will go away from theta side, and you'll be left with only
Okay.
theta. Then you will now take sine inverse of 0. So if you press the calculator, you press shift sine 0.375, you will get this 22.02. So because they are not asking you to look for sine theta, they're asking you to look for theta. So if you stop at sine theta, I think physics people, they will do it very well. They will leave the answer for your sine theta there. So they see people that will make people think that maybe they've gotten the answer. But if you know, you should know that you're not asked for sine theta, you're asked for theta. So you should take the sine inverse of the angle. So when you take the sine
So
inverse of
you
that
do
0 point, shift
so you
sine
do shift sign
0.375.
0.375.
Mm,
Give it 22.02. Okay, thank you very much.
yeah, you're welcome. Any other question before we call it a wrap?
So don't be angry. So that same thing we'll do for the total and internal reflection, see? Hmm? Okay, no. Don't
For
worry, I
the
get that one. Sorry. Sorry,
okay,
that's a mistake.
okay,
Yeah, I guess it.
no problem. So that will be all for this evening's lesson. I think there's a portion that I'm supposed to still explain, but we'll start that portion in the next class before we go forward. So that will be all for this. I think that should be all.
Yes, sir,
So
that's all. Thank you very much, sir.
yeah, good night, everyone.
Good night, sir. Take care of yourself. It's good though.